So we're going to work through the following problems today, just some of them listed here. And in particular, I'm going to choose some of the more important and slightly more challenging problems. Okay, some of these look pretty easy, but when you get down to them, they're not that simple. So we're going to work through them together. And I'm going to start with 22. Now, 22, if I do one part of 22, it should give you some insight into how to do 21, okay? 21's fairly involved for a tutorial, but I'm just going to illustrate 22, and you can perform the methods on 21. So, 22, determine whether or not the following pairs of curves intersect. Now, I'm actually going to choose the first question, part A. And in that case, if they do intersect, find the angle between the two curves at each point of intersection. Now, what do we mean by the angle of intersection? Well, the angle of intersection is determined by the angle between the tangent vectors. Okay, so you've got two curves intersecting. At that point, they'll each have a tangent vector, as long as they're smooth. We define the angle between the two curves at the point of intersection as the angle between the tangent vectors. So let's go through and calculate that and see how we go. Now, one mistake that people make with these kind of problems is they set the components equal and don't change, they keep the same variables, okay? Now, that's fraught with danger. So, 22. Okay. So, my first vector function is just going to be this. So, what's this? What's the graph associated with this going to be? What's the curve going to be? A line, yep. And now I'm going to switch to a second variable, u. Now I guess we're sort of implicitly understanding that it's defined for all t and all u, but really we're only interested in the intersection. So our curves intersect. When the components are equal, right? So when t equals u, t equals u squared, t equals u cubed. So from those equations, we've got to come up with, or find some value of t and u. So what I'm going to do is sort of use these two and make a substitution. Okay, so I guess I'll eliminate u. So I'll get t equals t cubed, so t cubed minus t equals 0. So I can factorise that, take out a t and then factorise. So on the surface, it looks like I've got three t values. T equals 0, t equals 1, and t equals minus 1. But can anyone suggest why should I ignore the t equals minus 1 from this? Yeah, it doesn't satisfy this because t equals u squared, so t's can't be negative, right? It's something squared. So our t points of interest are t equals 0 and t equals 1. So let's find the point of intersection associated with t equals 0 and t equals 1. Well, let's go up to here. Our points of intersection. All right, so let's go up to here and put in t equals 0. We'll get 0, 0, 0, t equals 1, 1, 1, 1. Okay. Did you go to the wrong room? Sorry. We just started, so you're not missing too much. So now the next question is, what's the angle between the tangent vectors at the points of intersection? Okay, so let's calculate that. So okay, so let's calculate the tangent vectors and then use the dot product involving the cosine to calculate the angle between them. Okay, so let's calculate the derivative and the derivative here. So differentiating component-wise manner, we're just going to get a constant vector. And over here, we're going to get 1, 2u, and 3u squared. Okay, well, at our point of interest, I guess t equals 0 corresponds to that point, t equals 1 corresponds to that point, but what about u? Well, I can go back up to here, and if I want to, I can get the corresponding u value. So when t equals 0, I can determine u is going to be 0 from up here, and when t equals 1, u is also going to equal 1. So let's work out our angle. So let's, for this case, let θ1 be the angle. We know that it's calculated from the dot product divided by the product of the lengths or the magnitudes. So this is at r sub 2. Okay, so 1, 1, 1 dotted with this at u equals 0. The length of that's going to be root 3, and the length of that's just going to be 1, right? So if I expand that, I'll get 1 on root 3. So all I've got to do now is take the inverse cos. So the angle of intersection, θ1, is going to be inverse cos of 1 on root 3. I'm just going to leave it like that. What about the other point of intersection? T equals 1. Okay, so cos theta 2 is just, again, the same thing. So it's going to be 1, 1, 1 dotted. But this time, when t equals 1, u equals 1. So I'm going to get a different vector up there. Okay, this is going to be root 14. Okay, so you work that out, take the inverse cos. Sort of running out of room here. It's a pretty standard question. In fact, I've seen that question on previous class tests for this subject. Okay, so that's a reasonable level. A reasonable level. You can see there's a fair bit of calculation involved. Questions? Okay. Let's move on to another one. I'm going to have a go at 24. 24 is a good one because it asks you about arc length, and that is reasonably likely on something like a class test. Okay, this is something that we want you to know. We want you to know how to calculate the length of a curve using vector calculus. That's something that we want you to know. Okay, so let's have a look at. I'm going to do 24 part B actually. I'll leave A for you to do. All right, so here we've got the following vector function. What is it? 2 log t, 2t, half t squared. And t is between 1 and 2. Now, it's not clear what kind of curve that is, but we don't really have to worry about that. Unless it's a really obvious curve, we don't really need to worry about it. Okay, so we know that the arc length is given by the following. In the vector format. So here our A would be 1, our B would be 2, and our vector function's written up the top. So let's call the arc length L. So let's calculate the derivative. It's going to be 2 on t, 2 and t. So the magnitude of that vector function is just that squared, well, I guess each component squared added together. Now, this is a good chance to pause and think, okay, I'm going to have to integrate that bottom line. So it's hard to integrate things with square root signs in them, in general. So what we would like to do is manage away the square root sign. Okay, so I'm going to expand it, but you might already see what's required here. Can anybody see how we can simplify what's in the square root sign? Sorry? Oh, that's not bad. Even simple. Well, I guess. So you're looking to factorise, right? Yeah. So it's exactly right. So one good idea here is to try to turn this into the square of something. Okay. Now I've got to admit, we wouldn't give you questions that were just horrible to integrate. So you should be looking for the square of something inside that square root sign. So if I write it like this, hopefully the penny will drop. Now, Convince yourself that that's okay, that the algebra is okay for that. What it means is I can just get rid of the square root sign, and because t is between 1 and 2, I don't have to worry about absolute values or anything like that. So that's what I'll get. So let's finish the problem. So I'm integrating from 1 to 2 of t on, t plus 2 on t dt. So we can integrate that hopefully, and I'm going to get something like this. Okay, so all I need to do is sub in 2 and 1, and I'll get something like this. Okay, that's a good problem. We want you to be able to calculate the arc length using vector methods, vector valued functions. All right, I'm going to have a go at 26. Anyone done 26? Let me put it up for you. Anyone done it? Yeah? Good. It's a hard question. Okay, 26 is a hard question. So part A is not that hard. Part B is a little bit more involved. Part A, show that for a particle moving with a velocity v, if the dot product of v with its derivative is 0, then the speed is constant. Well, let's have a look and see what we can see. So this is 26. What we want to do is show, sorry. So this is the speed, right? So how did you do it? Oh, sorry, no, not 0, constant. Sorry, show the speed's constant. Constant. Okay. Yes. How did you do it? Okay. Okay. All right. What about techniques from this course? Anyone? So we want to show that if this is true, then the speed's constant. Well, what can I do with that? I was just talking about it in a previous question. Can I collapse that down to something? The derivative of something? Yes. Now, the left-hand side is just half times the derivative of this. Just the product rule. It's just the product rule. There's that identity again. Okay, it's a really important identity. We've seen it twice today in kind of similar forms. So, what can I do? Well, I can get rid of that half. Sorry? No, because if you differentiate, so if you differentiate v prime, you'd get v double prime somewhere in there.
Because that's what you were last time.
Yeah, no. Well, no, it was it was R dash dotted with R double dash. Last time. Right. Yeah, you with me? It's just that now we've only got one derivative, whereas before we had two. So yeah, but the principle's the same. So I can get rid of that half and then just integrate both sides. Okay. Say some constant k. So if I want to just look at the speed, well, I'll just take the square root and define that to be a new constant. So, okay, so I'm defining a new constant there. Root k, that's going to be my constant c. So, therefore, the velocity is constant for all t. So that's another example where this kind of relationship pops up. It's really powerful. Anyway, last one. I'm going to do part B. 26 part B. Anyone? Yeah, 26 part B. Anyone done it? Yes. Yes, using F equals ma, something like that. Oh, what? Physics? Huh? Oh, I'm going to use F equals ma, so maybe I'm using a little bit of physics now. All right, so so we've got a particle of mass m with this position vector at time t. It's acted on by this force. Now the force involves some constant, lambda, and the cross product of the vectors involving the position and the velocity. Show that the speed v of the particle is constant. So this is a little bit more involved than the previous question, but let's see how we go. Right, 26 part B. All right. So, now the challenge is to show that the speed is constant, right? So how do we do it? Any ideas? Yep. Because we're talking about speed here. Okay, so if you know the velocity, you can calculate the speed by looking at the magnitude. Yep. All right. Any ideas how we might solve this? We've got a cross product. Okay. Oh, now you're talking. Oh. Prime? Yes. Oh. Oh. I don't think you need to rearrange it, to be quite honest. I think you're on the right track there. It sounds good. I think my method's a little simpler, but I think you're on the right track. Okay? Let me show you what I've done. All right. All right, so we know from physics F equals ma, right? Now, what I'm going to do is actually take both sides here and dot it with the velocity vector. Okay, so I'm going to take both sides of this and dot it with a velocity vector and just rearrange it. Well, I guess I probably should put in t's here, right? So let me just clean that up. Now, the left-hand side, what's the relationship between the acceleration and the velocity? Well, the acceleration is just the derivative of the velocity. So the left-hand side is just, oh my God. And the right-hand side, well, we can take our q from up here. Now, two questions. What's the value of the right-hand side? It's a scalar triple product. Who can tell me that's value? Zero, yes. Why?
Because of previous question.
Well, yeah, yes, or, right?
It's just the scale of time.
It's the same thing, right? Yeah, or if you want to think of it in real simple terms, remember the scalar triple product gives you the volume of a parallelepiped with sort of base vectors and then a height vector, right? That's like where are we? That's the height vector. But it's the same as this. So this is like, in a real simple version, this is like the volume of a parallelepiped with no height. So it's got to be zero. Okay, because these have got to lie in the same plane. It's the same thing. So the right-hand side 0, and the left-hand side is just m times a half. Yep, you guessed it. So what do we know? We integrate, we'll get a constant. So the speed has got to equal a constant. Not bad, huh? Not too bad. So that's 3 examples where this little derivative has popped up. It's really important in this section of the course. Okay, I think I'll leave it there, guys. I'll see you all next week. Don't forget to check your email for the new rooms and new lecture theatres.